So here we'll take another look at another question which involves an incline, so not level ground and not starting just horizontal, but an inclined plane. And this time we'll be looking to solve different things. We're looking to solve the time it hits the slope, which shouldn't be too difficult. And then secondly, we want to find when it hits the velocity. So things that we've talked about earlier, and we'll just apply it now to this question. So in this particular question, you've got a particle projected horizontally, as shown here, from a point O over here, with speed capital V, down a slope, incline at angle alpha. Now, alpha is given, it's tan inverse of a half. And this is below the horizontal. The particle moves in a vertical plane under gravity, where the acceleration due to gravity is g meters per second, which basically means projectile motion. At time t seconds, the horizontal and vertical displacements are given by x equals vt and y equals negative half gt squared. Very standard, except for the incline, going downward at tan alpha. So, show that it hits the slope at v over g seconds. All right, so our own diagram here might be beneficial. So let's quickly do one. And so your projectile will be heading sort of like this and hitting it at somewhere here. Let's label some points. We've got 0. They've called that x. Let's label this p, and that's y. And alpha, remember, keep in mind all your important information. So alpha is tan inverse of a half. It is a known angle. And it's below the horizontal, of course. X equals vt. Theta, if you want to think about theta, which is your launch angle, is 0 degrees, is the launch angle. And your y must equal negative a half gt squared, based on the fact that theta is 0. So show that the particle hits the slope after time v over g seconds. So when it comes to an incline, it's very useful to have an idea of what that incline is. So remember, as an incline, it's going through the origin, so it's a y equals mx line. So it's going through the origin, it's y equals mx. But this m is represented by tan of alpha. But note that alpha is an acute angle. Tan inverse of a half is like a positive angle, but it's going down. So using their terminology, it will be negative tan alpha x. Basically, or if you like, you would think of it as like alpha is a negative angle, but they've chosen to make alpha a positive angle, but just going downwards. So we will then need to put a negative in front. So it's a downward sloping curve at angle alpha. So y equals negative tan alpha x. And in fact, we know what tan alpha is because alpha is tan inverse of half. So this is negative half x. But we know specifically what this line is. This is negative half x. Now, you want to find the time where it lands. So you want to find this t. Okay, so, well, at this point, let's call this point, it's going to land at some a, b, where b is negative, okay? Note b is negative because it's below the x-axis. But our relationship is the fact that because it's y equals negative half x, then another way we can think about this is it's going to be a negative a over 2. Because, I mean, it's on the line y equals negative half x. So if x equals a, then b is just going to be negative a over 2. So we don't know what a is, but we do know that there's this relationship at impact. And we do know what x is at some time t. So we know that when x equals a must equal v times capital T that we're trying to solve for. And we know negative a over 2, which is the y, must equal negative a half g capital T squared. And we just now need to solve for t. Well, this is not that hard to solve because after all, the negatives cancel and the halves cancel. So, and then you just got a on the left. So in other words, we now have v capital T equals gt squared. So if capital T equals not equal to 0, so that's at the start, then that means v must equal gt, which means capital T must equal v over g. And that is what they wanted us to show. The particle hits the slope at time t equals v over g seconds. And that's how we do that. The next part of the question asks us to show that the particle hits the slope with velocity v root 2 meters per second at an angle of 45 degrees. So basically, they want you to show at the time of impact, your velocity is 45. Okay, so I haven't drawn it like so, but they're basically asking you to prove that it's 45 degrees to the horizontal, which it doesn't look like at all in my diagram, at velocity equals v root 2. So whenever you're asked to find the velocity in basically midair or at impact, you basically have two ways to do it. You can do it the parametric way or the Cartesian way. And there's no real reason to do it the Cartesian way in this question because we haven't got any of the, we haven't realistically been preparing to do that. So in this case, it makes much more sense to do it the parametric way, which of course utilizes the fact that x equals vt and y equals negative a half gt squared. You've got your displacements, just get your components. So horizontal component is v. The component in this case, of course, changes. So it's negative gt. But we know at impact, t equals v over g. So that means x dot equals v because, of course, constant velocity. And y dot equals negative g times g over v. So it's negative v. So what that then means is at impact, the velocity looks like this. Capital V across, negative v going down. And that's your horizontal component and your vertical components. So your total velocity will then be going like that. This is your velocity. So your velocity as a magnitude is just going to be the square root of v squared across plus v, well, negative v all squared, which is of course the square root 2 times v, which is what they wanted. Angle beta, well, tan of beta is negative b over v, absolute value, as in, which is negative 1, or is 1. So beta must equal 45 degrees, which is to the, well, it's to both the horizontal and the vertical. If it's 45 to the horizontal, it's also 45 to the vertical. I mean, I probably should have just, in hindsight, I probably should have solved for gamma. It wouldn't have made a difference. But because the question did say to the vertical, I probably should have solved for the angle to the vertical to be more direct with the question. But as you can see over here, we've got the velocity magnitude. We've got the angle representing, showing that it's going to be 45 degrees. And that's basically how you do velocity questions in midair and on impact at any particular time. And that's basically how you do this question.